Prim's algorithm using binary heap. Prim's algorithm is a greedy algorithm used for finding minimum spanning tree of a weighted, connected and undirected graph. In the last two lectures, we learned about Prim's algorithm and there we considered that input is provided as an adjacency matrix. And what is the time complexity of Prim's algorithm that we found? We found out that time complexity is order of v square, where v is the number of vertices. The question is there a possibility to improve on this time complexity? So coming to any algorithm which takes a graph as input, you have two options for providing the input. One is this graph can be provided using adjacency matrix representation, and other option is you can provide it using adjacency list representation. In the previous lecture, we had considered an adjacency matrix input of graph. This time, we'll be considering adjacency list input and then we'll see if we can bring up any improvement on the time complexity. So in order to do this, we'll be making use of binary heap data structure. When it was adjacency matrix, we did not use any heap. We simply used the distance array and we tried to track it out. But this time, we'll be looking into binary heap data structure and using it, we'll implement this greedy algorithm. So let us see how exactly we'll implement Prim's algorithm using a binary heap. First question is, this is a greedy algorithm. So what is the greedy strategy here? In Prim's algorithm, you always select the lowest weighted edge which is connecting any vertex which is already part of the minimum spanning tree to another vertex which is not yet a part of minimum spanning tree. So how did you decide on the vertices which are already part of minimum spanning tree? You initially started from any arbitrary vertex, any vertex, and then you kept adding one vertex and so on to this list of minimum spanning tree. So at any point, you will be having some vertices which you have already picked to the minimum spanning tree. And then if you want to pick the next vertex, what will you do? You will try to find that edge which is having minimum weight and is connecting one vertex on this side to one vertex on the other side. That is, this side is already part of MST, other side is not yet a part of MST. Okay, so let us see exactly how we are to go through these steps. So the first thing, you have to choose any arbitrary starting vertex. So any starting vertex. In Kruskal's algorithm, we used a starting edge, and in that case, we had to use the minimum weighted edge itself as the starting edge. But in case of Prim's algorithm, because we are considering vertex and not edge, we are free to choose any vertex because we know that all the vertices are part of MST. In case of edge, the problem was that not all edges are part of MST. Only some edges will be part of actual MST. Because of that, you can't add any arbitrary edge onto the MST. But here, because you're considering vertices, you are free to choose any arbitrary starting vertex because all the vertices of your graph will anyway be part of the MST. Okay. So let us say you chose some starting vertex. Next step is you want to initialize a min heap. You should have a min heap. Why are you having this min heap? This min heap is what we'll use in order to find minimum weighted edge. What is the property of min heap? Whichever is the element that is at the root, this will be the minimum weighted element among all the elements that are part of the heap. This is the min heap property, because of which it is easier for you to always choose the minimum weighted edge if you maintain a min heap. This is why we are using min heap here. So how exactly do we make sure that this edge is connecting one vertex in MST to another vertex which is outside MST? This we'll get back to, okay? As of now, just understand that min heap is useful for finding minimum weighted edge. The next thing, we have to store each of the edges onto min heap. So how are we going to store? We should be using the weight of this edge as the key. That is, based on the key, sorting will be done. Not exactly sorting, the min heap structure will be maintained based on this key. So the key will be weight of the edge. So you can say you have many edges of a graph. Let us say your graph is something like this. You have A, B, C, D, E, and you have some weights like 1, 2, 3, 2, 1, so on. Then you will say, let us say you have an edge AB. AB is of weight 1. Similarly, BD is of weight 3. So whenever you have edges like this, each node in this heap will represent an edge, and the key used will be the weight of this edge. So whichever is having lowest key, that will become root of your min heap. This is how it will work. So each entry in the min heap will represent an edge in the graph. This is how your min heap will be maintained. Initially, your heap will be empty. Slowly, you will be populating this heap. So what will you do? Initially, you have a min heap and you should be having a visited array. Why should you have this visited array? This visited array should be Boolean. It should be a Boolean array. There will be entry corresponding to each of the vertices of your graph. And this will be either true or false. If it is true, that means this particular vertex is already visited. Already visited means this vertex is already part of your MST. And if it is false, that means you are yet to visit this vertex. Yet to visit means it is yet not part of MST. Means you have to still take it to the MST side. So these are the initializations that you want to do. Then all edges that are connected to the starting vertex, initially what you will do, you will consider that whatever is your starting vertex, let us say this is your starting vertex. So your starting vertex is already part of MST. This is an arbitrary choice. You can choose any vertex as your starting vertex. You will anyway get MST. You can pick any vertex from your graph. So your starting vertex, for that you will make visited as true. For all other vertices, visited will be false, which means those are yet not part of MST. And what about the heap? Onto the heap, you should add all edges which are directly connected to the starting vertex. Let us say this is you have the starting vertex, and from starting vertex you have edges to some other vertices. So all these edges, these should be added to your min heap. So as of now, whatever are the entrants of min heap, those entries will be edges which are directly connected to starting vertex. So once you have all the edges which are connected to starting vertex added to the min heap, now you can start with, okay, let me write this step. Third step is you have to add all edges. One is you have to identify starting vertex. You identified that. Then you have a min heap which is presently empty. Then you should have a visited array which is all Boolean, and you should have true value for starting vertex, false for all others. And what is the third step? Third step is add all edges which are directly connected to the starting vertex to this min heap. Okay, so you are adding all those edges to min heap. Once you add it, remember that the key should be weight of that edge. Based on the weight, you should be prioritizing those edges. After this, you have to repeatedly follow few steps. What is those? Let us say you want to repeat. You have to repeat until you have visited all edges, okay, all vertices. So what you have to do is, first thing, you have to extract whichever is the smallest edge, or you can say edge or vertex Here we are considering that we are putting edges onto the min heap. So extract smallest weighted edge from this min heap. How do you do that? Simply extract the root, because root of the min heap will be having lowest weight. So what will you do? In order to extract the smallest edge, you simply have to take the root. What will you do? Once you see the root, let us say root is, let us say, some edge AB. What will you do now? You know A is the starting vertex, B is the ending vertex. You will check whether A and B are such that one among them should be part of MST and the other one should not be part of MST. Then only this particular edge can be selected. Why is this so? Why is this that one should be part of starting vertex and other should be not? It is because Prim's algorithm is based on cut property. We had already discussed this in previous lectures, that because we are depending on this cut property, we are depending on the fact that one side of the cut will be having MST vertices and the other side of the cut will be having non-MST vertices, which means whichever be the smallest edge which is crossing this cut, that cut will always be part of the MST. Because of this, it is safe to add the smallest edge which is part of this cut to the MST. This is the logic. So let us say you got edge AB as the smallest weighted edge. What will you do? You have to verify that this edge is such that one vertex is on one side that is part of MST and the other vertex should be on the other side that is not yet a part of MST. How will you verify this? In order to verify this, you will check this visited array. What will you do with this visited array? If the value in visited array corresponding to both A and B are true, that means both of them are already part of MST, which means this edge should not be considered. What if both the values are false? If both the values are false, that means both these vertices are not a part of MST. Then also you should not consider this edge. But if it is so if it so happens that one of the vertices gives you a value true and the other vertex gives you a value false, that is in this visited array, that means one vertex is part of MST and the other vertex is yet not a part of MST and you want to add it, which means this is an edge which is crossing this cut and you have to add it to your minimum spanning tree. So considering that one vertex gives you the value true and the other vertex gives you the value false from this visited array, what should you do? You should mark unvisited vertex, that is among these whichever be the vertex that gave you false result. For that particular value, you should mark it as true in visited array. So in this visited array, whichever among A and B is the vertex which gave you false value, which means it is not yet part of MST, you should mark it as true, which means you are considering this vertex also as a part of MST from this point. And what is the next step? You have to add all edges connected to this newly visited vertex to min heap. You have to add all edges that are connected to this newly visited vertex, whichever be your newly visited vertex, all the edges connected to it should be added to added to min heap. Why should you add it to min heap? Because when are you adding any edge to this min heap? You are adding it when you know this edge should be considered. When will you consider? You will consider whenever one among the vertices of this edge is a part of MST. That is when you will consider. Then you can ask me a question. The question is, why are you making this check whenever you are taking this particular edge out of MST, out of min heap? If I'm adding it to min heap only when one among the vertex is part of MST and other is not a part of MST, then why am I making this check when I'm taking it back from min heap? The reason is you're simply adding all of these to min heap. And let us say in the next few steps, it is so possible that among any of the added edges, the other vertex may also become a part of min heap in any of the other steps. At a later stage, you may again be calling this vertex, which is having one edge, which was previously having one edge in MST, one vertex in MST and one vertex out of MST. But now, let us say by the time you take it back from heap, you may have crossed, let us say, some 4-5 steps. And by this time, maybe both of the vertices are now part of MST. So in order to make sure that in this situation, you can skip this edge, that is why we are having this check again when you're taking it out of this min heap. Okay. So when you are inserting to min heap, you will be inserting whenever you are considering any vertex which is not in min heap, not in MST, to be part of MST. Whenever you are doing this consideration, you will be adding it to min heap. Okay. What will you be adding? You will be adding all the edges which are connected to this newly identified vertex, that is newly identified vertex in the non-MST set. You will be marking it to the MST set, and then you will be adding all the neighboring vertices, all the edges which are directly connected to this vertex. So these are the steps, and till what point should you do? You should continue repeating this till the point you have all the vertices as visited. That is, in your visited array, you should have true value for all the entries. Or another way of understanding this is whenever you have already v-1 vertices, v-1 edges as part of MST. So in your MST, you'll be maintaining an MST set as well. In this MST, you will be adding edges whenever you want to, you select any new edge onto the MST. So whenever this edge count reaches v-1, that means your spanning tree is already built. So you can terminate your process at that point. So let us just understand these steps clearly, and then we'll go into time complexity analysis. So our steps are, initially you can select any arbitrary starting vertex. Then you should have an empty min heap and an Boolean visited array. In this visited array, all the values will be false, and whichever is the starting vertex for that particular index, you will give a true index. That is, value will be true, which means only the starting vertex is part of MST when you are starting with the algorithm. Then all the edges which are directly connected to the starting vertex, they will be added to your min heap. So you have a min heap structure in which you will be adding all the edges which are directly connected to your starting vertex. Then you should repeat these steps till the point your MST is complete. That is, till the point you have v-1 edges in your MST, or another way of understanding it is till the point you have all entries as true in your visited array, whatever be the situation. So what are the steps to be repeated iteratively? You have to extract the smallest edge from this min heap. That is, you have to extract root from this min heap. Then what should you do? You should verify that this particular root, whatever you have extracted, is having one vertex in MST and one vertex out of MST. That is, for one vertex of this edge, value should be true here, and for the other vertex, it should be false in the visited array. So array is indexed. You can directly go to that index and check whether this particular vertex is having true value or if it is having false value. Once you verify that it is having true for one vertex and false for other, that is, it is crossing from MST set to the non-MST set, then you can add this particular vertex which is not in MST set to the MST set. Or you can say whichever be the edge under consideration, this edge will be added to the MST. So what should you do for that? You should first mark true in the visited array for whichever was not visited. That is, whichever was the vertex which is not in MST, you are putting that vertex into the MST set. And then you have to add all the edges which are connected to that vertex in the min heap. So this is how you are adding all those edges onto min heap. So you will have all those new edges in the min heap. Again, you will repeat the same process. You will extract the smaller, whichever is the smallest edge. You will continue with the same thing. You will check whether it is crossing from MST set to the non-MST set. If it is crossing, you will add it to the MST. Add that edge to the MST. Again, both those vertices get converted to MST vertex. Again, you will continue this process till the point your MST is complete. That is V minus 1 edges are complete. Let us see what are the time and space complexities in this case. Let us see time complexity first. In time complexity analysis, this starting vertex, it doesn't take much time. These are not time taking operations. You are simply initializing a heap and then you are having a Boolean array. Then let us say you are adding all the edges which are related to the starting vertex into the min heap. So if you want to add one edge onto the min heap, let us say even if you consider that this min heap is already having all the edges and still you want to add one more edge, it will take only order of log e time for addition. So it should not be much time. At max it can be e log e if you want to add all the edges again. Okay, this is the worst case for addition. Then next thing is you want to repeat these steps again and again. So one more thing is here, if you are doing a build heap process, it is going to take maximum of order of n time. So it won't be much, that is order of e. So it's not much time though. Even if you consider that you are adding each edge newly, then also it will take only order of e log e. Then this repeated steps, this is where you have to concentrate on. First thing is you want to extract the minimum edge from the min heap. So extraction means you just have to take the root out from the min heap. So if you want to take the root, this part is simple, but then you have to again heapify this. So this thing will take order of log e time, considering that there are e edges. And if you consider that all the e edges are already there in the heap, still, if you want to do a reheapify, that is going to take order of e. So extracting the minimum element will take order of log e time. And how many times do you want to extract this? You may want to do this for each edge once. Why is it? Because MST will be having maximum v minus 1 edges. Then why should you do for e times? The reason is there may be many edges in this heap which are not part of MST. So you may have to extract it and then skip this. So this situation also arises. Because of that, in worst case, you have to go through all the edges once. So which means e times you have to do this log e operation, which means total will be order of e log e for this extract minimum. Total number of times this extract minimum will be called into the time taken for each extract minimum. The total is order of e log e. What is the other time consuming operation? If you want to mark as true, this will take only order of 1 time. So e times order of 1 will be order of e in total. And what about adding all the edges which are connected to min heap, connected to this vertex to the min heap? This adding will again take order of log e time. And in worst case, how many edges will you have to add? So you will have to add, in worst case, totally, if you consider complete loop, throughout the all loops, maximum is that you will have to add all edges which are part of this graph. So maximum is order of e times you will have to do this order of log e operation. So total is order of e log e. So you understood that the worst case time complexity for this Prim's algorithm is order of e log e. One thing to note here is, in some places you may see it as order of e log v as well. Why is it order of e log v? The reason is, in worst case, e can be order of v square. And whenever you're talking about v square, Order of v and order of v square are very different. You have to specifically consider this as different. But what if it is log v? If it is log v and log v square, both are one and the same as far as time complexity is concerned. The reason is log v square can be written as 2 log v. So 2 log v and log v are both of the same order, because of which e can be written as v square, which is of the order of log v only. So log e and log v are the same. See, e and v are not same, those are different, but log e and log v are of the same order. So as far as time complexity is concerned, you can always write either log e or log v because both are of the same order. Okay. So you can either write e log e or e log v, both are right. So the next thing is, what is the space complexity? Space complexity, what are the space consuming operations here? One is for the min heap. In the min heap, in worst case, you may be having all the edges in the min heap, which will take order of e space. So whatever be the number of edges, those many entries may be there in min heap and order of e space may be taken. Then what about this visited array? It will have all the vertices, which means order of v space will be required. And again for the MST, you may have to store the MST. MST will have maximum v minus 1 edges. So order of v space will be taken for MST as well. So in total, you have order of e and order of v, whichever is larger, that is order of e plus v is the space complexity of this Prim's algorithm. So the next question is, which representation should we use? In the previous lecture, we had seen that you can achieve time complexity of order of v square when you are having adjacency matrix representation. Here, with adjacency list representation, you were able to achieve order of e log v. Then one question is, why am I specifically saying that adjacency list you should use this representation and adjacency matrix you should use this representation? The reason is, in case of adjacency matrix, we had seen that there is no point in using binary heap because anyway finding all the neighboring vertices will take up order of v time. So order of v into order of v will anyway become order of v square. So gaining some time during extract operation is not going to be handy in case of adjacency matrix representation. But when is adjacency list and you want to find all the edges that are connected to a vertex, you can simply go to the entry corresponding to that vertex and you can see all the adjacency list, that is all the entries in the linked list corresponding to that vertex. You will get all the neighbors. So because of this, in adjacency list representation, identifying all the neighbors will not take order of v time. Instead, it will take order of e time in total if you consider all the loops, not for each step. If you consider total time taken for this step in all the loops, it will take only order of e times. And each time you want to do whatever operation. Here it is log e operation. So because of that, in case of adjacency list representation, order of e log e is much beneficial. Then the question is, when should you use which representation? Whenever your graph is a dense graph. That is, what is a dense graph? In a dense graph, you will have a lot of edges. That is, if you are having some vertices and a lot of edges in this graph, let us say here and there you have a lot of edges. In that case, that is a dense graph. What happens is, number of edges will be order of v square. So if you use an order of e log e algorithm, that will be order of v square log v. So if you convert, order of e log e will become v square log v. So in such cases, when you have a dense graph, it is better to go with adjacency matrix representation and use order of v square time complexity, because v square log v is even larger. So using v square time complexity using adjacency matrix representation is better in such cases. But in case you are having a sparse graph means E will be order of V, that is number of edges will be comparable to the number of vertices. In such cases, adjacency matrix representation time complexity will remain as order of V square, but adjacency list representation, if you use binary heap data structure, then time complexity will be order of V log V. Why is it V log V? Because E is order of V when you're having a sparse graph. Here, V log V is better than V square. Because of that, whenever you have a sparse graph, adjacency list representation and this binary heap based implementation of Prim's algorithm is better option. So your time complexity, just considering this binary heap representation and adjacency list representation and binary heap data structure, Prim's algorithm will take order of E log V time and order of E plus V space.